So far we've seen some of these familiar vocabulary words at play with some of these common sugars. The next thing we're going to look at is a new functional group and anomeric carbon on this quadrant here where we see structures. So you can see up here, here's D-glucose, and here it is written in what we call a Fischer projection. It's straight. But then if you notice these equilibrium arrows, what actually happens with glucose in our blood, in our bodies, is it goes from straight into a ring, and it opens up and straight and into a ring. And it's in an equilibrium going back and forth between straight and closed rings. And there's actually two different ways it can close up. It can close this way, or it can close this way. And so we'll look at describing a couple of features of that. So these structures are all in equilibrium with each other, and they each have their separate uses in the body. Looking first at this glucose here, this is what we saw above. It was an aldose, right, with that aldehyde on top of it. When this closes up, I get a new functional group, and that's going to be my hemiacetal. So a hemiacetal, when I read it, is going to be an O, and then a C, and then an OH, and that H might be a clue that you're going to use a hemiacetal. So if I look right here, here's a hemiacetal. It goes O, C, OH, and here's that carbon in the middle. All right, so that is a hemiacetal, and then over here I can see an O to C to OH. So this is a hemiacetal over in this ring. And you notice that even though they have an OCOH, they have a different three-dimensional orientation. So we need a way to describe that. And the way to describe that is going to be this alpha and this beta. All right. So if I can look at the O and then the C and then the OH, I can think about I'm going down to catch that O, and that down is my alpha. So if the hydroxyl is pointed down in the hemiacetal, it's an alpha D-glucose. Over here, if the hydroxyl is pointed up, you can see it pointing up here, then I think of that as a little balloon for beta. And so the hydroxyl floating up is a beta glucose, and the hydroxyl pointing down is an alpha. And that would be true for other sugars that closed up too, not just a glucose. So every sugar has this open closed kind of orientation, and every sugar would close as an alpha or could close as a beta instead. So you need to be able to recognize those. We would call these two structures anomers of each other. So they are an isomer, same molecular formula, but in their own kind of separate category of anomer. And we talk about the anomeric carbon. The anomeric carbon is going to be the one that we look at to define if I have the alpha or the beta arrangement of the hydroxyl. So the center carbon in a hemiacetal is my anomeric carbon, that middle carbon there. And I look at the hydroxyl orientation around it. This is also going to play a role, we'll see when we start to name some links. We need to be able to find this anomeric carbon, and it's going to play a role with some numbers that we use to name these. The other thing I want to draw your attention to on this page is some reactions here. So we've seen these reactions before, just smaller molecules. So the first thing I'm going to do is tend to ignore some of these lines of hydroxyls and just look at what is changing as I go through here. So here you might notice from this glucose to sorbitol, my top of my molecule changes, and then I might notice on this second one that I have this ketone show up, and so this part of the molecule changed. So I want to ignore the other stuff and just focus in on what's changing. So I'm doing that with highlighters. So as I look at this, I can see that I go from an aldehyde to an alcohol, and in the process of doing that, I gain hydrogen. We know that going from an aldehyde to an alcohol, I gain 2 hydrogens, but you don't actually even have to count here. You just have to notice, hey, hydrogen showed up. And so then I bounce back to glucose to put my label on it, and I would say this molecule became reduced because it gained those hydrogens. And then we've got a chemical that's really similar to the NAD that we've seen before, NADPH. Remember, this is the reactant going in, and then here's my product coming out, the NAD+. So this lost a hydrogen, which means that it was oxidized. Remember, you can also put the agents. This is the oxidizing agent. This is the reducing agent, and all of those labels fall to the left. They fall with the reactants of this reaction. Another hint that might be helpful here, this says aldose reductase, and so that enzyme name tells you a lot, right? It tells you start with an aldehyde, and it tells you you're going to reduce it, so that can be kind of a good hint. So that's looking at this first reaction here. Let's take a look at the second reaction from sorbitol to fructose. So ignoring this, now I'm going to notice that this alcohol becomes a ketone, and I want to double check that nothing else changes. So that's my key change here. So as I go from here to here, I see that I lose 2 hydrogens, which the enzyme name tells you, dehydrogenase. When I lose 2 hydrogens, I'm thinking, okay, that's oxidation. And so my label comes over here to sorbitol, and I say sorbitol, this is for this reaction here, is oxidized as it goes that way. Means it's the reducing agent. And then if I look at NAD, which is the coenzyme helper here, the NAD picked up a hydrogen, so the NAD was reduced and would be the oxidizing agent. So those are the labels for this reaction, and then this reduced label was for the first reaction. So given these molecules now, you don't have to necessarily predict the products, but you need to be able to look at them and figure out, here's the important part of the molecule that changed.